Hi again. Welcome to section 2.5. So in section 5, we're going to show derivatives of formulas. So in this section, we'll get the derivative formulas that will let us find formulas for derivatives when a function comes to us as a formula. This is a very algebraic section, and you should get lots of practice. When you tell someone you have studied calculus, this is one skill they will expect you to have. And they're talking about algebra. So this is where algebra really starts, and you've got to pay attention. There's not a lot of deep meaning here. These are strictly algebraic rules. So we are not going to think about anything except how to implement these rules. So we have some building blocks. These are the simplest rules for basic functions. We won't prove the rules, we'll just use them. But first, let's look at a few so we can see that they make sense. So here we have, find the derivative of y equals f of x, which is mx plus b. So this is a linear function. What that means is it graphs to a line. And it doesn't matter where the line is, it has a constant rate of change. And that rate of change is the slope. So if I have y equals mx plus b, my derivative of any linear function is the slope. Okay? So rule 1, the derivative of a linear function is its slope. Or example 2 and rule 2 as well. If we want to find the derivative of f of x equals 135, so we would have a graph that looks like this. This is f of x equals 135 if this point right here is 135. So let's look at this as a graph, and we can see that the line is horizontal. So what would its slope be? If I say rise over run, it's not rising, so it's 0 over anything is 0. So that gives us another rule. The derivative of any constant is 0. Now we have find the derivative of f of x equals x squared. This question is challenging using limits. We will show you it the long way, or I will, and then give you a shorthand rule to bypass all this. So basically, I'm going to do algebra, and I'm going to show you how I get from x squared to the derivative of x squared. And then we'll talk about what the derivative is. So I can say this is equal to the limit as h approaches 0 of, well, f of x plus h. We've talked about this a few times. We replace whatever the x is with what's in the parentheses. So it's x plus h quantity squared. So if f of x equals x squared, then f of x plus h equals x plus h squared. So I can just plug this in now. F of x plus h is x plus h squared minus f of x, x squared, divided by h. This equals the limit as h approaches 0. Now, you always have to write that limit there. And then if we multiply x plus h times x plus h, we get x squared plus 2xh plus h squared. So I'm going to put that in here, x squared plus 2xh plus h squared minus x squared divided by h, which is equal to the limit as h approaches 0. Well, usually I would say take your parentheses off first, but there's nothing to do to these. We could just actually cancel the parentheses. They're not important. And then we can say x squared minus x squared is 0. So we get just 2xh plus h squared over h, which equals the limit as h approaches 0. I can factor out my h. I get 2x plus h divided by h. I can cancel my h's, and I get that the limit as h approaches 0 of 2x plus h equals 2x. So what does that tell me? Well, it basically tells me what the derivative of x squared is, but we have a more general rule. Our general rule is called our power rule. I think we'll see this again. And our power rule says if f of x is equal to x to any value, could be fractions, it could be pretty much anything, then the derivative of this function would equal n times x to the n minus 1. All right, we'll be using all of these. Don't be concerned. So luckily, there's a handy rule to skip using the limit, which is what I just said. So here we have it. The power rule is exactly as I just stated. So now I want to find the derivative of g of x equals 4x cubed. Well, I'm actually going to give you the rule first this time, because unless I prove it to you, I'm just going to state that this is true. And then you're going to have to believe me, or else you're welcome to come to see me in my office hours, and I will be happy to prove it's true. How's that? Maybe that's an incentive for you to come visit me. All right. So it says rule, constants come along for the ride. So if I have the derivative of a constant times a function, that's equal to the constant times the derivative of the function, which is exactly what this says. Okay, so what does this mean? The rule says that constants come along for the ride. So basically, here's a constant inside the derivative. I can take it outside the derivative, and I can say the derivative of a constant times a function is equal to the constant times the derivative of the function. So in practice, what that means is I have g of x equals 4x to the third. So I can say dg dx or dg of x, it doesn't matter, either's fine, is equal to 4 times the derivative of x to the third with respect to x. That's all I'm really doing, is taking the derivative of that. Well, that's the power rule. So we can say this is 4. Let's say h is equal to x to the third. So I'm taking my 4 out, and then I want to take the derivative of h as a function, which equals 3x squared. How did I get that? Well, if I have f of x equals x to the third, then f prime of x is equal to 3, because this is n, times x to the n minus 1, which is equal to 3x squared. Okay, so then I put that in here. The derivative of x cubed is 3x squared. We get 12x squared. And that's really all there is to it. Just always take the constants out. It'll save you a lot of worry and trouble. Right. derivative building blocks. So we have the constant multiple rule. We just talked about it. If I have the derivative of a constant times a function, it's equal to the constant times the derivative of the function. We just went over that. The sum and difference rule, all that really means is that I can either, if I have something plus something or something minus something, I can pull them apart and take the derivative of each thing individually. I have the power rule that says x to the n equals nx to the n minus 1. We just talked about that. And here we have special cases. The derivative of k, which is just a constant, is 0. We showed you that, or I showed you that. The derivative of x is equal to 1 because basically what this says, if I have x to the 1 and I use my power rule to take the derivative, I have 1x to the 0 power, which is 1 times 1, which equals 1. Anything to the 0 power is 1. So that handles that. The derivative of e to the x is e to the x. I'm not going to explain it in this class, but just trust me, it's true. And here we have the derivative of any constant to a variable is equal to ln of a times a to the x. So basically, these are exactly the same if a equals e. A to the x, because that's always going to be there, then times the natural log of the base. So if the base is e, we're replacing a equals e, we get e to the x, ln of e, and hopefully you remember ln of e equals 1. 1 times e to the x is e to the x. And there we have it. And another one that's kind of weird that you won't be used to is the derivative of the natural log is 1 over x. Just take my word for it. So the sum, difference, and constant multiple rule combined with the power rule allow us to easily find the derivatives of any polynomial. So let's say I want to find the derivative of this. So I'm going to say p prime of x. Well, remember, we're going to take the constant out, and then we're going to multiply by, we have 10, x to the 10th. So here, n equals 10. So we have n x to the n minus 1 times 17 plus 13 times the derivative of x to the 8th, which is 8x to the 7th, plus, minus 1.8 times x, but the derivative of x is 1, so times 1, and then the derivative of every constant is 0. So let's put this all together. We have 170 x to the 9th power plus 104 x to the 7th power minus 1.8. And that's it. Not too bad. We just used, we used the constant rule, the constant multiple rule, and the power rule. Let's look at some more examples. So you don't have to show every single step. Do be careful when you're first working with the rules, but pretty soon you'll be able to just write the derivative directly. So again, we're going to say f prime or d of this dx means exactly the same. I'm just using that for shorthand. So that's going to be 17 times the derivative of x squared, which is 2x, minus 33. I don't care about the constant, I take them out. The derivative of 1, we said, the derivative of x, we said, is 1. And the derivative of every constant is 0. Here we get 34x minus 33. And that's the derivative. So the power rule works even if the power is negative or a fraction. In order to apply it, first translate all roots and basic rational expressions into exponents. For example, what they mean is y equals 3, and t, the square root of t is the same as t to the 1/2 power minus 4. When t to the 4th is in the denominator, if I were to move it to the numerator, it would change sign in the exponent. And then plus 5e to the t. Sorry, I couldn't tell. All right, so let's start. This equals 3 times, remember the power rule is if f of x equals x to the n, the derivative is equal to x n to the n minus 1. So I have, well, n is here, n is 1/2, so I have 1/2 t to the 1/2 minus 1, which is negative 1/2, minus 4 times, now we have the derivative of t to the minus 4. We can still use this formula. We get minus 4 t to the minus 4 minus 1, which is minus 5, plus 5 times the derivative of e to the t. Well, e to the t, derivative of e to the t is just e to the t. So let's make this all go back into some form that we understand better. And this equals 3/2 times 1 over t to the 1/2. 16 t to the minus 5. So minus 4 times minus 4 is plus 16. And then t to the minus 5. Plus 5e to the t. This is the same as 3 over 2 times the square root of t plus 16 over t to the 5th plus 5e to the t. And that's it. That's our answer. If you have any problems with any of these, please feel free to stop by my office hours or write me an email and we'll set up some office hours. Find the equation of the tangent line. This says a little bit something different because we're looking for an equation that's going to be y equals mx plus b. That's the equation of a line. We also have one other equation of a line, which is the one we're most often going to use, which is y minus y1 equals m times x minus x1. Okay, so let's see which one works better here. Just choose whatever works better. So they're telling us that we have this function, which is called g of t, and it's equal to minus t squared. So we know g of t equals 10 minus t squared. And then g prime of t, well, again, the derivative of a constant is 0. So I have minus, and then I use my power rule on this. So this becomes 2t to the 1 power, which is just 2t. And that's what we really just use. Okay, now we're given some additional information. We want to know what the equation of the line tangent to this curve is right at this point. So we plug in t equals 2. So g prime of 2 is equal to negative 2 times 2, which equals negative 4. Well, that looks pretty good because there's definitely a negative slope there. So now that we have our slope, And we know a point, we have this point 2, 6. So why can't we use this form? Because that form gives me y minus, well, we only have one y, so that must be y1. So that's 6 equals m. Here's m. That's the derivative. So negative 4 times x minus this 2. And you can leave it like this. This is the equation of the line tangent to the curve when t equals 2. Unless someone says put it in slope-intercept form, you can definitely leave it in point slope. They're both very valid. And this one's much easier. You could even use this equation and solve for y, and you would have the y equals mx plus b. I'll do it for you. So if I add 6 to both sides, I get negative 4 times x minus 2 plus 6, which equals, let's distribute, negative 4x plus 8 plus 6, which equals negative 4x plus 14. There's my y. So this line, this red line, is actually got a y-intercept of 14 and a slope still of negative 4. That's not changing. So that is, you could use the point slope to change into slope-intercept if you wanted. All right, the cost to produce x items is equal to the square root of x in hundreds of dollars. So let's not forget that. It says A, what is the cost for producing 100 items? Well, C of 100 is equal to the square root of 100, which equals $100, which is a very weird thing to say. We don't say that. So we write 10 and then hundreds. If I have 10 hundreds, so here's 100, and I multiply this by 10, which just adds a 0. So I have that the cost for producing 100 items is $1,000. The cost for producing 101 items, 10.049887. I'm going to stop there. $100, right? Which is equal to 1004.9. And if we're talking about money, we can only round, we have to round it to 2 decimal places. So if I'm going to round it to 2 decimal places, then, and remember, I'm multiplying by 100 because we have that many hundreds. So this would be the new decimal point, and this is my rounding to 2 decimal places. I look to the right, it's a 7, so that 8 becomes a 9. So this is the cost for producing 101 items. This is cost for producing 100 items. So the cost of producing the 101st item, so the cost to produce the 101st item is equal to, really, what's the difference? $4.99. Okay. Let's do B. So we have B. And B says f of x is equal to the square root of x. And we want to find f prime of x. So if f of x equals the square root of x, next thing would be f of x equals x to the 1/2 power, because that's what the square root equals. If you're not sure how that happened, try watching the exponential lecture. If that doesn't help, come see me. So now we have the power rule, which says that f prime of x is equal to nx to the n minus 1. So that equals 1/2 x to the 1/2 minus 1 is minus 1/2, which equals 1/2 times the square root of x. That's it. Now, if we want to know what f prime of, so now I'm about right. So first we calculated it, we just got it. Evaluated at x equals 100. That's pretty easy. We get 1/2 times the square root of 100, which is equal to 1/2 times 10, which is equal to 1/20, which equals 0.05. Hundreds. Don't forget, we're using hundreds. So 0.05 times 100 is going to give me $5. Well, when we just estimated, it was $4.99. But when we actually take the derivative, we get $5. We can live with that. It's so close. We're okay with it. Okay? Actually, your book gives it to you different. I'm going to give it to you this way first. So if I have the product of two functions, f of x times g of x, it's equal to, I always remember it as f prime g plus g prime f, but this is how they give it to you, which is exactly the same. They just change the f and g, so that f is always first. So basically, we take the derivative of the first times the second plus the derivative of the second times the first. We're going to do some examples. So we can say if we have the derivative of a quotient, notice it's f prime g, exactly the same, minus fg prime. This is plus, the same thing as this is minus, and then we divide by the function squared. The numerator of the result resembles the product rule, but there is a minus instead of a plus. The minus sign goes with the g prime. The denominator is simply the square of the original denominator, no derivatives. So for example, here's a product rule. How do I know? Because I have two functions that are multiplying together. So here's my recommendations to make things very nice and clear. I always do this, I always teach this way. So let's say we have small f is equal to e to the t. Then f prime is e to the t. And let's say g is equal to ln of t. G prime, I don't know if you remember this, is equal to 1/t. Now I know my formula, f prime g plus I use g prime f. You can use whichever way you like. So, and then I just plug stuff in. So e to the f prime is e to the t times g ln of t. Okay, so f prime g plus, now I'm going to g prime 1/t times f, e to the t. So this is g prime f. Now we're going to simplify this. How am I going to simplify this? I'm going to say, well, I have two terms that have e to the t. So I'm going to factor that out, and I get ln of t plus 1 over t, and that's really my best answer. But if you notice, it's very nice to have all this over here so that you can just work through the problem. I have a product rule. So we can just do it. So it says find the derivative. I'm going to say, actually, since I'm using g here, I can say u equals 4x cubed minus 11, and du dx is equal to 4 times 3x squared, which equals 12x squared. And I also have, I'll use u and v, equals x plus 3, and dv dx, or u prime v prime, either one. Here, I'll do it both ways, u prime, v prime. This is equal to the derivative of x is 1. The derivative of 3 is 0. So v prime equals 1. Okay, so since I changed it from f's and g's to u's and v's, it's going to be u prime v plus v prime u. Does it matter which order? No, everything's positive here. So u prime is 12x squared times v x plus 3 plus v prime, just 1, times u, which is 4x cubed minus 11. Okay, this is u prime v times v prime u. We can multiply all this out and see if we can combine any like terms. So we get 12x to the third plus 36x squared plus 4x cubed minus 11. I can combine 12x cubed and 4x cubed, and I get 16x cubed. I don't have any other x squareds, so I'm going to cancel these, plus 36x squared, done, minus 11, complete. So that is how you use the product rule. I really recommend this technique over here, where you find your derivatives first and then you just plug them in. Up to you. Now suppose we want to find the derivative of this. Well, this function is not a simple sum or difference of polynomials. It's the product of polynomials. We could simply multiply it all out to find its derivative as before. I didn't do that before I used the product rule. Who wants to volunteer? Nobody. Who's going to want to multiply these together? I mean, I'd do it if I had to, but there's a better way. So I'm going to do it two different ways. So there's one more type of complicated function that we want to know how to differentiate the composition. Remember when we talked about composition and decomposition, we had like an inner function and an outer function. It's back. So basically with this, since we don't have the chain rule yet in our pocket, and the chain rule is going to apply here, it always applies. We've just never talked about it. So we could always just multiply these together. 4x cubed plus 15x times 4x cubed plus 15x, which is equal to 16 x to the 6th. First times first. Outer times outer plus inner times inner are the same. So it's 15 times 4 is 60, and we have 2 of those. So that's 120 x to the 4th. That's outer times outer plus inner. And then plus last times last, which is 225 x squared. And now we could find the derivative. Remember, it's easy from here. Take out the constant, use the product rule, which is 6n to the 5th, plus 120 times 4x to the 3rd. This is not an n, this is an x. Sorry about that. Yes, plus 225 times 2x. So we multiply this out, we get 96x to the 5th plus 480 x cubed plus 450x, and I found my derivative. Say we want to find the derivative of 4x cubed plus 15x to the 20th power. Well, if I were to multiply that all out, I'd have 4x cubed plus 15x times 4x cubed plus 15x 20 times. And I don't think any of us want to do that. So we have this easier way. I'm going to show you my way. I'm going to show you I'm going to show you 2 different ways. I recommend if you're getting confused, use the way I'm going to show you. Let's look at our chain rule. The chain rule is the most common place for students to make mistakes. Yes, it is. Part of the reason is that the notation takes a little getting used to. And part of the reason is that students often forget to use it when they should. So you can just assume that there is always a chain rule. Every time you take a derivative, there's a chain rule. Some of it you won't see right now, some of it you'll see later, some of it you'll see right now. So the one that I mostly like to use will probably be your least favorite, but once I show it to you and you get the hang of it, it'll be your most favorite. And that is this one, number 1. And basically, this is why it's called the chain rule, because I'm chaining a bunch of functions together. So look at how this goes. If I were to cancel these, I would have dy dx. So that's why it works. We can, with the first notation, which is again my favorite, and my favorite for complicated functions, but my favorite for easy functions is b, using prime notation. So what this says is that if I want to take the derivative of x, I might have some u value in there. So actually, this is pretty complicated the way they have it written. So let me rewrite this as, if I want to take the derivative of f of g of x, it's equal to the derivative, while I put g of x in here, times the derivative of the inside function. And we'll talk more about inside and outside functions. We've already talked about it before, we'll talk about it again. The chain rule in words: the derivative of a composition is the derivative of the outside and the inside staying the same times the derivative of what's on the inside. So I think I'll show you this in 2 different ways right now. I'm just going to break this in half. And I'm going to say my inner function I'll call g of x, is equal to 4x cubed plus 15x. And my outer function, which I'll call f of x, is equal to x squared. And if I find the composition of these, I'll have, so let's call it h of x is equal to f of g of x. So now what they're telling me is that h prime of x is equal to f prime of g of x, whatever was there, times g prime of x. So that's the outer inner thing. Let's do it for this problem. We'll get h prime of x is equal to, well, f prime, f is equal to x squared, so that's 2 times, well, g of x is my new x right now, so 4x cubed plus 15x. So notice that is the derivative of, this is the derivative of the outer function. The outer function has the inner function embedded in it, times the derivative of the inside function, which I'll put down here, times the derivative of g prime of x, which is 4x cubed plus 15x. So that's 12x squared, 4 times 3x squared, plus 15. And then I can multiply this out. I get 8x cubed plus 30x times 12x squared plus 15. And I don't know if you want me to do this or not, but sure, let's do it. So I do multiplication a little differently. I think I may or may not have shown this to you. I'm not sure, but I usually do it vertically. And this may not even be worth it, but I still do it vertically. First term, and I multiply it by this and then by this. So let's see what that means. It means 8 times 12 is 96, x to the 5th power, plus 8 times 15 is 120, x to the 3rd power. Okay, so now I've multiplied 8x cubed times both terms, just like you would do any kind of multiplication. If I said 75 times 23, you would multiply everything times the 75 times 3. So I get 15, carry the 1, 21, 22. And then I would move over 10, carry the 1, 15. And then I add. We're doing polynomial multiplication really the same way. It's just like FOIL, except usually it turns out nicer. Okay, now I got 8x cubed times both terms on the bottom. Now I'm going to multiply 30x times both terms on the bottom. And I'm just going to put them underneath where they belong. For example, 30 times 12 is 360. X cubed, why don't I just put it under here? 360x cubed. That way I don't have to go hunting for it later. And this is very nice when I have a lot more terms. And then I multiply 30x times 15, and I get plus 450x. So I can add down. Oh, I'm at the bottom here. I get 96 x to the 5th plus 480 x to the third plus 450 x. Okay, and you can FOIL it if you'd rather. And the only reason I'm even doing that is because I want to show you that they're the same. Now we're going to do it using, so that's the inner times the outer, okay? So the derivative of the outer times the derivative of the inner. Now I'm going to use the rule 1, which I think makes things usually a lot clearer. I hope it does. So I start with y equals 4x cubed plus 15x all to the second power. And now I'm going to make another little sidebar here. And I'm going to say, let's let u equal the inner function. Then I have du dx is equal to 12x squared plus 15. Hopefully by now you understand how I do that. Y equals u squared dy du is equal to 2u. Now, leave this notation says I can write this dy dx as being equal to dy du because I have dy du times du dx because I have du dx. And notice if I multiply those two together, the du's would cancel with each other, wouldn't they? And I would end up with dy dx. But that's not what my intention is here. I'm not canceling anything. All I'm doing is saying, okay, so that equals, well, dy du is 2u. And du dx is 12x squared plus 15. Now, I just have to say dy dx equals 2 times u. Here's my u. So it's 2 times 4x to the third plus 15x times du dx. And du dx is 12x squared plus 15. This is equal to 8x to the third plus 30x times 12x squared plus 15. And notice this is 8x to the third plus 30x times 12x squared plus 15. And notice this matches this, so they must have the same answer. So I just showed you that it works both ways. You will get the exact same answer both ways that you do it. All right. So let's try doing the chain rule one more time. I'm going to do it. I don't care. First I'll do f of g of x. So that's why this was important before. I'm going to make g of x equal 4x to the third plus 15x. And I'm going to make f of x equal x to the 20th power. And that g of x is going to go into where that x is. Okay? So if I want to do this using the second method, I would say the derivative of this function is equal to f prime of g of x times g of x. Okay? Now, this is equal to, I've already pretty much got things here. So f prime of g of x is equal to 20 times something to the 19th power. And what I plug in there is g of x. And then I'm going to multiply by g prime of x. If we have f of g of x, and we want to take the derivative of this, that's our formula. So f prime of g of x is 20, and then g of x to the 19th power, still a power rule, n. Here's my n, and here's my n minus 1. Then I need the derivative of g, which is g prime is equal to 12x squared plus 15. So 12x squared plus 15. So that's it. That's all you get. I'm not going to do anything with this. Okay, number 16. Now this one's a little hard to differentiate. I'm going to only use Leibniz on this. And then maybe I'll do Leibniz first, and then I'll show you how to do it with inside, outside. But it's just so hard to see inside and outside functions sometimes, unless you have a lot of experience. So when I look at this, I see I have e to the something, but I don't know how to take the derivative of e to the something. I know how to take the derivative of e to this x, or e to some one variable. So what I'm going to do is I'm going to say, let's let u equal x squared plus 5. Then du, the derivative of u with respect to x, is equal to, using the power rule, 2x plus 0, because the derivative of a constant is 0. So I have this information. And then I have here y equals e to the u. And dy du equals e to the u. E to the variable is e to the variable, right? So if I start with this and I want dy dx, that I can say is equal to dy du, because I have it. And then I need to get rid of that du, so I'm going to multiply by du. Oh, I have du dx. Oh, look at that. So I have my chain. I can see that the du's would cancel, even though we're not going to cancel them. So I have dy du, which is e to the u, times du dx, which is 2x. This gives me e to the u is x squared plus 5 times 2x. So you could write this as 2x e to the x squared plus 5. Now that we did this, I think I'll do the other one by showing you how this works. If you notice, I have e to some power. My outer function is e to the x, and my inner function is x squared plus 5. So I keep this the same because my outer function is, so here I'll write this. My outer would be e to the x. My inner would be x squared plus 5. And I'm just combining them by showing you the Leibniz. Example 17. The table gives values for f, f prime, g, and g prime at a number of points. use these values to determine the composition of f of g of x and f of g prime of x at x equals 1 and x equals 0. Okay, so let's start with f composed with g of x is equal to f of g of x. The derivative of f of g of x is the derivative of the outer function. So it's the derivative of the outer function, which is, the outer function here is f prime of g of x times the derivative of the inner function. Okay, so let's see what we can do here. F of g of x. Well, f of g of x is equal to f of, well, when x is -1, I'm going to use all these values first, right? But what goes in for g of x is 3. I now say when x is 3, f of x is 0. So this equals 0. So f of g equals 0. Then let's just erase this and this. And I can say when g of x equals 1, plug in 1. I go to my x at 1. F of x at 1 is equal to 1. So I plug that in. Next, I'll just keep using the same place. Next, I have g of x equals 0. So f of 0. I go here to where x equals 0. I pick -1 for f of 0. And then, almost done. Next, we have f of -1, which is equal to, now I go back up to the top, 2. So this is equal to 2. And last, g of x is equal to 2. So f of 2, I go here to where x equals 2, I find f of 2 equals 3. F composed with g of x, now we have to do the derivative. And we wrote it up here. The derivative of that function is f prime of g of x times g prime of x. This is equal to, well, when I plug in x equals -1, x equals -1. So first thing I do is I say this is f prime of g of -1 times g prime of -1. So this is equal to the derivative at g of -1. Well, at -1, g of x is equal to 3. Times the derivative of g of -1. So we have times 0, which anything times 0 is 0, so this is obviously 0. And the only other one they asked us to do is x equals 0. same thing. I have f prime of g of 0 times g prime of 0. Okay, well, g of 0, now I'm on this line when x equals 0. So here we go. F prime of g of 0, well, that's 1 right here. So g of x is 1. And then we have g prime of 0. G prime of 0 is times 2. But now what's f prime of 1? Well, now we have to go to a different line, because when x is 1, we're on this line. So f prime, which is this column, of 1 is equal to -1 right here. So this is equal to -1 times 2, which is equal to -2. We start this by saying I have a function times a function. So I know I have to use the product rule. So I'm going to say f of x is equal to e to the 3x. And I can say g of x is equal to ln of 5x plus 7. I need f prime of x, and I need g prime of x. But I don't like this notation because I don't know what the derivative of e to the 3x is, because there's some chain rule involved that I'm not sure what I'm doing with it. So let's try to do this. We'll say y equals e to the 3x. I'm going to let u equals 3x and du dx equals 3. Okay, so now I have y equals e to the u. And I know that dy du is equal to e to the u. Remember, it doesn't change. So if I want to know what, and that's why the notation, the Leibniz notation is so nice, find the derivative of f of x with respect to x. Okay, so dy dx is equal to dy du times du dx. Dy du is equal e to the u, and du dx is equal to 3 e to the u. So I say this is 3e, and I said u is equal to 3x. So to the 3x. And that is my df of x dx. 3e to the 3x. Okay. We got that part handled. Now we have to figure out what g prime of x is. So g of x is equal to ln of 5x plus 7. So I can say here dy du is equal to 1 over u. So I have dy du, I have du dx. So dy dx is equal to dy du times du dx, which is equal to, well, dy du is 1 over u. and du dx is 5. So let's continue. And I get that this dy dx is actually the derivative of g of x dx, which is equal to dy du, which is 1 over u, and u is 5x plus 7. I substituted that times 5. And now I have my g prime, which is 5 over 5x plus 7. Okay, so I've identified, so these right here, I did so that I could solve for f prime and g prime, because f prime and g prime all on their own were not simple derivatives. So now I have f, g, f prime, g prime, and I have, so the derivative of a product is f prime g plus g prime f, and now I can just substitute. F prime is 3e to the 3x, f prime, times g. I have ln of 5x plus 7. Then I have plus g prime. So now everything changes. And I get g prime times f. So g prime is 5 over 5x plus 7 times f, which is e to the 3x. This is actually my derivative, but we're going to clean it up a little. I'm going to get rid of this, and I'm going to get rid of this, and I'm going to say, okay, well, I notice that I have e to the 3x in both my terms. So I'm going to factor out e to the 3x. And then for this whole term, I have left 3 times ln of 5x plus 7. Plus, well, this is already factored out, and this is already factored out. So I get 5 over 5x plus 7. And that should be my final answer. So we have to differentiate this. What is the first thing it says? Don't panic. As you come in from the outside, what's the first thing you encounter? It's the fourth power. That tells you this is a composition, and it's a complicated function raised to the fourth power. The only way I would do this, honestly, is with Leibniz. So we start with z equals parentheses 3t to the third divided by e to the t times t minus 1. Okay, so we have a function divided by a product rule. So we need to go very slowly and carefully. So I'm going to say, because I have a quotient rule, I have f over g. So f is equal to 3t to the third, and f prime of x is pretty easy to find, 9x squared. I have g, which is equal to e to the t times t minus 1. Well, that's a product rule. So let's kind of step down here and say, for my product rule, we have y equals e to the t times t minus 1. I'm going to set u equal to e to the t, which gives me du dx, or du dt, sorry, is equal to e to the t. And I'm going to say v equals t minus 1. So dv dt is just going to equal 1. So no worries. If I have to use the product rule on this function, I could say it's u, the derivative of u times v plus the derivative of v times u. And we have the derivative of u is e to the t times v, t minus 1, plus the derivative of v, oh, that's 1, times u, e to the t. So now I found the derivative of this, which equals this. So g prime of x is equal to, and again, I think it's always easier when you factor stuff out. Let me simplify this. I'm going to factor out an e to the t, and then I have t minus 1. That gives me my first term, and then to give me my second term, I have plus 1. So this, now look at that. T minus 1 plus 1 is just t. So this becomes t e to the t power. And that's my g prime, t e to the t power. So if I were to try to explain what I did here, first I said I have a quotient rule and I need my f, g, f prime, g prime. So this is for the quotient rule. Well, I can find the derivative of everything except this g of x, because there's another product rule there. So this I broke down into pieces for a product rule. And here I just really continued the algebra of the product rule. So now let's see. I have, oh, I missed something here. This is to the 4th power, right? Yeah. Okay, let's see what we get. Actually, I'm going to have to kind of go this way, I think. So now we have f over g, and we want to find the derivative of that. That would give me the derivative of my inside function, wouldn't it? So let's see what we get. Well, we have a quotient rule. F prime g minus g prime f over g squared. I go back up here and I just simply plug things in. And when I say simply plug things in, I know this is really complicated. I'm so happy to help you all if you come to see me, or just request anytime, and I will do my best to fill your request. So f prime, 9x squared, times g. G is e to the t times t minus 1, minus g prime is t e to the t times, so g prime f, 3t cubed. sorry, I'm getting so smushy in there. Okay. That whole thing is going to be divided by g squared. And we said g is e to the t times t minus 1. E to the t times t minus 1, this whole thing squared. So I know that looks nasty, and if you can't simplify anymore, I understand, but I'm going to still simplify as much as I can. E to the t, which I found in both my terms. And what do I have left? 9 t squared times t minus 1. And then minus, well, I already factored out my e to the t, so I have 3 t to the 4th power. There's a t here, here's a t here, and here's 3 t's here. I'm going to divide this entire thing. Well, first let me close my parentheses. I'm going to divide this whole thing by e to the t times t minus 1 quantity squared. All right, so this equals e to the t times 9t to the 3rd minus 9t squared minus 3t to the 4th divided by, and everything in here is squared, so I can say this is e to the t times e to the t times t minus 1 times t minus 1. And we'll see if that helps us any. Well, it helps a little because I can cancel out one of these e to the t's. And I can also now factor out a 3 from everywhere. This gives me 3 times 3t to the 3rd minus 3t squared minus t to the 4th divided by e to the t times, I'm just going to leave this as t minus 1 squared, and I may be able to factor more things, but I think that's going to do it. So this is really the derivative of my inside function. We can't forget what this is. This is my inside function, the derivative. Now, if I go back up to the top, I say z is equal to, okay, I'm just going to put a little piece in here. So I'm going to say, we've used U's and V's and F's and G's too much. So let's say W is equal to 3t to the 3rd over e to the t times t minus 1. All right. And we know that at the bottom here, we actually have dw dt because we found all the derivatives of everything on the inside function. So w to the 4th power. And I know how to take the derivative of that, right? dz dw is equal to 4w to the 3rd power. I got lots of chains happening here, so I want to find dz dt because this is my z as a function of t. Well, I have dz dw. I have dw dt. And if I cancel the dw's, I get dz dt, so I'm on the right track. dz dw equals 4w cubed times dw dt. Well, let's copy it. We have 3 times 3t cubed minus 3t squared minus t to the fourth divided by e to the t times t minus 1 squared. This equals 4 times. Well, w. I think I'm going to get lazy here and copy and paste. All right, perfect. So there we have it. Look, we take the outer function, we took the derivative 4, we use the inside piece as the w, and then to the third power. And then last, we have to multiply that by that other part of the function. Let's see. I'm going to write it all up right here. So I have dz dt is equal to 4. So 4 times 3t cubed over e to the t times t minus 1, that whole thing to the third power, times, and I've got 3. I'm going to take this 3 that comes from here, and I'm going to multiply it by that 4, which gives me, instead of 4 here, it gives me 4 times 3 is 12. I can let go of this 3 because I just multiplied it on the outside. So now I have times 3t to the third minus 3t squared minus t to the fourth divided by e to the t times t minus 1 squared. And honestly, that's fine. I don't want to simplify it anymore. There's still many ways I could simplify this, but I think that's good enough for now. And in our finale, okay, so what if the derivative doesn't exist? So a function is called differentiable at a point if its derivative exists at that point. We've been acting as if derivatives exist everywhere for every function. This is true for most of the functions that you will run into in this class, but there are some common places where the derivative doesn't exist. Remember that the derivative is the slope of the tangent line to the curve. That's what to think about. So where can a slope not exist? If the tangent line is vertical, the derivative doesn't exist. It says show that f of x, which is equal to the cube root of x, which is equal to x to 1/3, is not differentiable at x equals 0. So that means I have dy dx is equal to the power rule says 1/3 times x to the 1/3 minus 1, which is equal to 1/3 x to the minus 2/3, which is equal to 1/3 x to the 2/3, which is good enough, actually. We don't have to turn it into a radical. If this is my derivative, it is not differentiable at x equals 0, because at x equals 0, the slope is equal to 1/0, which does not exist and is not differentiable. So where can a tangent line not exist? If there's a sharp corner. So this is basically what you have to look for. Corners, cusps. So a corner looks like this absolute value. A cusp would be something like a graph that had like this thing, something where it kind of looks like that. The derivative will not exist at a point at those points because there's no well-defined tangent line, a teetering tangent, if you will. If there's a jump in the graph, but that's not continuous, so we know that we can't take the derivative. The tangent line will be different on either side of either side, and the derivative cannot exist. So jumps, no. Sharp corners, no. Cusps, no. And okay, this is the last problem. It just says, show that f of x equals the absolute value of x is not differentiable at x equals 0. So that's right here, right? I'm just going to read it to you. And then I'll explain it if it doesn't sound clear. On the left side of the graph, the slope of the line is -1. That makes sense. We have x, if we can say the absolute value of x can be divided into a piecewise function. We can say it's x when x is greater than or equal to 0, and negative x when x is less than 0. So I can see that when x is less than 0, my slope is -1, because this is really y. So y equals minus x means that m equals -1. And when it's greater than or equal to 0, well, actually for the graph, we're going to say we don't know what it is at 0. When it's greater than 0, we know. For y equal x, m equals +1. So m equals +1. And how would we figure it out? How would we figure out, sorry, this should be -1. How would we figure out what it is at 0? Because it's coming in at such a sharp corner that we can't find the derivative there. I think I've said this before. I'll say it again. I don't know if it'll be for the last time, probably not. We want smooth and continuous functions if we want to take the derivative. And you'll get used to those terms. So, all right, I think we're complete. Thanks for watching, and have a good one.